Okay, so 32. So 32 reads for 1.4. The numerical equation a squared equals 1 has exactly 2 solutions. Find at least 8 solutions of the matrix equation a squared is equal to I sub 3. Okay, 8 solutions. Okay, find at least 8 solutions. Okay, and so the suggestion is that you look off the main if you look at matrices where it's 0 everywhere outside of the main diagonal. So if we look at so I sub 3 is a 3 by 3 matrix. So what we want is our A matrix to be 3 by 3. And we're going to look at matrices where everything off the main diagonal is 0. Now we want the square of the matrix to be the 3 by 3 identity matrix. So the first choice is A there. You see that when you square that A, you get I sub 3? Maybe you forgot what I sub 3 is. I sub 3, or I sub 3 is the 3 by 3 identity matrix. So I sub 3 is just actually the exact matrix I just wrote down. This is I sub 3. That's I sub 3. So do you see how if I square that A, I get I sub 3?
Yeah, because it would be the same thing.
Okay, good. So now you just need to think of another 7 more 3 by 3 matrices that's square to give you I sub 3. So I'm going to copy that. So again, off the main diagonal, we're going to make everything 0. And so we're only going to think about what entries in the main diagonal should be. So how about this? Why not make all of them -1? You see that when you square it? When you square that, you'll end up just squaring all the these entries. So -1 squared is 1. And when you square the matrices, you'll get the identity. Does that make sense?
Yeah.
So like, for example, you don't just square them. You're actually multiplying. You're multiplying the matrices, but the effect is the same as when you multiply those two matrices. When you do the operation of multiplication, you'll end up with this. Okay. So that's the second choice. And so you need 6 more. So another choice you can do is just, I deleted it, didn't I? Wait. Okay. Recording in progress. I want to copy this. Okay. So now you can just alternate. So for instance, this could be 1, that could be 1, that could be -1. And when you square that, you also get I sub 3. Do you see that?
Oh, I get it. So it's just pretty much you pick whichever -1 in the main diagonal and you just choose different ones for it.
So you just alternate between 1 and -1 on the main diagonal. Okay. You have 2 choices for each entry. Either each entry would be 1 or -1. So you have 2 choices and there's 3 entries. So 2 times 2 times 2, there's 8.
Okay.
That make sense?
Yeah, thank you. I just wasn't sure what I was asking before.
Okay, but now you see it?
Yeah, thanks.
So either they're all 1s, they're all -1s. One of them is a -1, or 2 of them are -1s. So, or two of them are -1s. I just have to get it to the next line. Or 2 of them are -1s, or all 3 of them. Oh, I already did all 3 of them -1. Oh, okay, so that fits. I'm gonna minus something on my screen here. This is gonna be. There we go. So I now have 8. Those are all 8. Those are 8 ways to get the square to be I sub 3. Okay, so that's 32. So that makes sense now. Okay, so the other one you said you had a question about was number 13, right?
Yeah.
Okay, so for number 13, verify that the equations are valid for these matrices. Okay, so you want to verify this equation. A BC inverse is equal to C inverse, B inverse, A inverse. So it says verify for the matrices in 5 to 8. Okay, so so that's just saying basically okay, so let's choose one of them. You know what, let me choose the fourth one. So oh wait, 5. Okay, so just choose 3 of the matrices then. Oh, so you have, okay,
I
so
think
then,
because it says A, B, C, A, B, and C. So 5 would be A, and then 6 would be B, and 7 is the one for C.
okay, well, I was just gonna, so I'm just saying, you could just choose the and the test is, you won't have a problem with this. I'm gonna choose the A as being the A in the book. So it's gonna be 2, -3, 4, 4. And then B is going to be the B in the book. So B is going to be 3, 1, 5, 2. And C is going to be 2, 0, 0, 3. 2, 0, 0, 3. Okay, so and then you just verify it for that. So you can ask yourself, what is ABC? So ABC is equal to the product of these 3 matrices. So it's A times B times C. And so that's just okay, so I'm going to multiply these 2 matrices first. And so if you multiply the first 2 matrices, you just get, so I'm going to have to do this quick. 6 minus 15 is -9 here. 2 minus 6 is -4. And then it's going to be 12 plus 20 is 32 here. And then it's going to be 4 plus 8 is 12 here. So when you multiply the first 2 matrices, you get that. This is still the matrix 2, 0, 0, 3. And so then when you multiply those 2 matrices, you'll get the 2 by 2 matrix, -18. Then you get -12. Here you get 64. And here you get 36. Okay, so that's ABC. And then if you take ABC inverse, you just want the inverse of that matrix. So to take the inverse, it's 1 over AD minus BC. So it's -18 times. So it's -18 times 36 minus -12 times 64. Okay, and then it's times the matrix you get by switching the diagonal entries and then negating the ones off the diagonal entry. So this is going to be a 36. This is going to be a -18. This is going to be negate -12, you get 12, negate 64, you get -64. Let's now, this is equal to 1 divided by, and so -18 times 36. So you have 9 times 4 times 9 times 2. That's 8 times 81. You have 648. So this is -648. Let me just check. So 20 times 360, 720 minus 72. That's 50. Yep, that's right. Okay, and so then it's plus, because 2 minuses is a plus 12 times 64. So 12 times 64. Okay, so you have 8 squared. You have 4 times 3. 8 squared is 4 squared times 2 squared.
You can
Oh wait,
put
it's
it
4 cubed. Sorry, 4
on down
cubed.
low.
Never mind. It's 256 times 3. So it's 762. So it's plus 762. Okay, please mute your mic,
Hit
please.
a cutter for a home run to right center. He hit a cutter and it was
Okay, so then so you have 64 times 6.
It was 768.
Yeah, okay, I'm just checking it now.
Yeah.
Okay, so 768 you're saying? So then okay,
Yeah.
so it's
Then that's 1 over
256.
120.
750. So what do you say?
Then it's 1 over 120.
Yeah.
Yeah.
Yeah, okay, I know. Alright, so then you have 1 over 120, and then so then you have times this matrix still. Oh, just copy it. Good. So it's 1 over 120 times this matrix, and that's equal to now the 2 by 2 matrix you get by dividing by 120 in every entry. So you have 36 over 120. You have 12 over 120, which is 1/10. You have negative 64 divided by 120, and you have negative 18 over 120. Okay, so that's ABC inverse. And then you just take the inverses of each of these three matrices, and then and so for short, it's 1/6 times that. So this is going to be 1/3. This is going to be 1/2, and that's going to be 0 and 0. That's C inverse. And then B inverse is equal to, okay, so 6 minus 5 is 1 over 1. And so, oh, wait, sorry. You switch, sorry, this is a 1/2 here, and that's a 1/3. Okay, so then for B inverse, when you do it, AD minus, you have 1 over 1 times, and you switch the diagonal entries, you negate ones off the main diagonal, get B inverse is that. And then A inverse, you just do each one individually. I have to do this quick. And then so A inverse, you have 8 minus negative 12. Oh, wait, wrong one. 8 minus negative 12 is 20. 1/20th. 1/20th times. Now you switch the entries in the main diagonal of A. You negate the off diagonal entries. So you have 3, -4. So you have 1/20th of that. So if you take 1/20th of that, then you get 1/5. You get 3/20ths. You get -1/5 and 1/10. So now that's A inverse, B inverse, and C inverse. And then you want to say C inverse times B inverse times A inverse. So you have C inverse times B inverse times A inverse. And that's equal to, and you see, just multiply these matrices. This matrix times this matrix times this matrix. And so then that's equal to, okay, we'll need that one. Okay, so you multiply the first two matrices here, and so you get 1 there, you get -1/2 here, you get -5/3 here, you get 1 here, and then it still times the other third matrix here. So I'm just gonna paste that times that matrix there. And so when you multiply those two matrices, I'm hoping we get the same answer, unless I made a calculation mistake. 1 + 1/10 is 11. 1/5, 2/10 plus 1/10 is 3. Oh, okay. So we have 1/5 plus 1/10 is 3/10. Okay, so now this is going to be equal, and I'm going to simplify this matrix now. Right, 36 over 120. If you divide numerator and denominator by 12, you get 3/10. That's the same. This is 1/10, which is in simplest form. 64. So 16 divided by 30, -8/15. -8/15 is in simplest form. And -9 over 60, 3 over 20, -3 divided by 20. So that's 3/10 is the same. This entry is the same. Here we have 3/10 minus, 3/20 minus 1/20 is 2/20, which is 1/10. Here we have -1/3 minus 1/5. That's -8/15. And then here we have -1/4 plus 1/10. So we have -6 over 40. Oh, there was a noise again. -1/4 plus 1/10. So we have -10 plus 4 over 40. We have -6 over 40, which is -3 over 20. Good. That's -3 over 20. Good. Okay, does that make sense? You couldn't follow private calculation, but basically you just do these calculations. ABC, the inverse of ABC is this, and C inverse, B inverse, A inverse is that, and they're the same. So what we have shown that ABC inverse is equal to C inverse, B inverse, A inverse for the given matrices ABC. Make sense?
Yeah, thank you. I was just a lot because like the fractions and like a lot of numerics involved. That's why. Thank you.
But you get it?
Yeah, thank you.
You're welcome.
There's a long
Okay,
process too that I thought for myself. That's why.
Okay. Okay. And now I'm going to go back to material. Okay. So, all right. So, So now let's keep going. So last class, we ended last class with finishing the material from, so we started 1.5, which is elementary matrices and methods for finding A inverse. Okay, so the goal was to develop an algorithm for finding the inverse of a matrix and to discuss some of the basic properties of invertible matrices. So I gave you 3 elementary row operations on a matrix A, right? Multiply a row by non-zero constant C, interchange 2 rows, and add a constant C times 1 row to another. And I emphasize the word another because this, as an elementary row operation, this changes the matrix, the row that you're referring to as another. So if you add 3 times 1 row, if you add 3 times row 1 to row 2, row 1 stays the same, and row 2 is what is changed by that operation. Okay, so it's the thing you're adding to that's changed. So if you add 3 times 1 row to another row, it's the another row that's being changed, and the original and the thing you're multiplying is actually not changing by that operation. Okay, now these 3 are just inverse operations. So if you apply one of these operations to a matrix, these are the corresponding inverse operations that will undo what you did. So if I interchange 2 rows, the opposite would be to interchange the same 2 rows to get back to where I started. If I multiplied a row by non-zero constant C, the opposite would be multiplying that same row by 1 over C. Right? If I multiply a row by 3 and then I multiply it by 1/3, I'm getting back to where I started. If I add 3 times 1 row to another row, and then I add -3 times that same row to that same other row, then I undo the effect that I originally had, right? So if I add 3 times row 1 to row 2, and then add -3 times row 1 to row 2, I now undid what I did, right? if you have, the analogy was better last class, but if I hand you 3 apples, the opposite would be taking away 3 apples, right? So, so in a sense, if I'm giving you 3 times a row, if I'm giving a row of the matrix 3 times another row, the opposite would be to take away 3 times that same row from that other same row. Okay? And so that's the idea, that's how this is the inverse operation. And so the conclusion we can draw from these elementary row operations and these inverse operations is that if you start with B, if you're given that a matrix B is obtained from A by performing a sequence of elementary row operations, these 3, then that implies that there's a second sequence of elementary row operations, which when applied to B recovers A. Okay? So if you start with the matrix A and you apply a sequence of elementary row operations on A, and at the end you end up with a matrix B, then there's a corresponding sequence of elementary row operations which undoes each of those operations one at a time in the reverse order until you get back to the A that you started with. Okay? So if you start with the matrix A and you do a sequence of elementary row operations to get a resulting matrix B, then you can just do the opposite. You can do the inverse elementary row operations in reverse order and get back to A. So if this is the first one, and this is the second one, and this is the third one, and this is the fourth one, and this is the fifth one, and then this is the nth elementary operation you have to do to get A, then n, and if n prime is, let's say, the inverse, or instead of writing n prime, I'll write n inverse. But I'm speaking loosely here, so what I mean is it's the inverse operation of this one. If I first perform the inverse of the n dot dot dot, then the inverse of the fifth operation, then the inverse of the fourth one, then the inverse of the third one, and the inverse of the second one, and then last, the inverse of the first one, I get back to A. Okay, I'm just undoing the effect each of these had in the appropriate order to get back to where I started. So that was the conclusion that we ended last class on. Okay, so this class we're continuing from there. Okay, so we're going to start with a definition. Definition. Matrices A and B are said to be row equivalent if either and hence each can be obtained, if either can be obtained from the other by a sequence of elementary row operations. Okay, so A and B are said to be equivalent if either and hence each can be obtained from the other by a sequence of elementary row operations. That's a definition of row equivalent matrices. 2 matrices are row equivalent if either of them can be obtained from the other by a sequence of elementary row operations. So here, A and B are row equivalent. Okay, so here, B is obtained from A by a sequence of elementary row operations. So B is row equivalent to A. Knowing that B is row equivalent to A, then tells us that we can find inverse operations that, when applied in reverse order, gets us back to A. So A is also row equivalent to B. So knowing that B is row equivalent to A, that we can find a sequence of elementary row operations getting us from A to B, means that if we do the inverse operations in reverse order, meaning instead of the first to nth, we do the inverse of the nth to the inverse of the first, we can go from B to A. And so A row equivalent to B implies B is row equivalent to A. B is row equivalent to A implies A is row equivalent to B. And so instead of saying one matrix is row equivalent to the other, you just say that they're both row equivalent to each other. Okay? So we say two matrices are row equivalent to each other instead of saying one is row equivalent to the other. Okay, the order doesn't matter. Okay, another definition. A matrix E is called an elementary matrix if it can be obtained from an identity matrix by performing exactly one or a single elementary row operation. On it, meaning on the identity. So matrix E is called an elementary matrix if it can be obtained from an identity matrix by performing exactly one or a single elementary row operation on it. Okay, so let's look at example one is elementary row operations. Elementary matrices and row operations. Okay, so on the left, I'm going to put an elementary matrix. On the right, I'm going to put the operation that produced it. Okay, so the first matrix is a 2x2 matrix. It's a 2x2 elementary matrix, which is 1, 0, 0, minus 3. And so the operation that produced it was just, the operation that produced is just multiplying the second row of I sub 2 by -3. I could have just written I there, but I'm just explaining it. So I've added some details that maybe I didn't need to say. So I might just say I there, but I wrote I sub 2 to say the 2x2 identity matrix for you. So I multiplied the second row of I sub 2 by -3. That's exactly one row operation on an identity matrix, which means that this is an elementary matrix. Okay, another matrix. This is the third one in the book, so I'm going to call it 3. Okay, so then this matrix is 3 by 3, and it's 1, 0, 3, 0, 1, 0, 0, 0, 1. And so this matrix is adding 3 times row 3 to row 1. Okay. Of I sub 3. Okay. So if you start with I sub 3 and you add 3 times row 3 to row 1, you get this matrix. Right? If you have we go to the whiteboard. So I sub 3, this is I sub 3. That's I sub 3. Now, if I add 3 times row 3 to row 1, so add 3 times row 3 to row 1. Okay, so I'm going to add 3 times row 3 to row 1. Then what happens? Well, so actually first I'm going to color this in green. So I'm going to add 3 times this row to the first row. So first off, the second row stays exactly the same, right? And actually I'm adding 3 times row 3 to row 1. So row 3 is not going to change either. I'm adding 3 times row 3 to row 1. So it's the row 1. It's this guy that changes. Okay? Because it's 2. Add 3 times row 3 to row 1. Row 1 is the only thing that changes. And so what changes is I'm going to have to add 3 times this row, that one. Well, if I add 3 times 0 to 1, it's still 1. If I had 3 times 0 to 0, it's still 0. If I had 3 times 1, which is 3 to 0, I get 3. So this resulting matrix is an elementary matrix. Okay, it resulted in one elementary row operation from an identity matrix. So that's an elementary matrix. And so that's why here I have that as an elementary matrix. Okay, another interesting example of an elementary matrix is this 3 by 3 matrix. And there'd be more than one way to describe this as an elementary matrix. This is also an elementary matrix because I can multiply the first row of I sub 3 by 1. So if I multiply the first row of I sub 3 by 1, that's an elementary row operation. I'm multiplying a row by non-zero constant, namely 1. Even though it doesn't change the matrix, I still performed an elementary row, exactly one elementary row operation on an identity matrix. So an identity matrix is also an elementary matrix. And so note that 4 is illustrating the fourth example here above is illustrating an idea. Is illustrating that it only said for that, but it's true for any. So I'm talking about more generally here than that. But the fourth above is illustrating the more general statement that every identity matrix is also an elementary matrix. Okay? If you take any identity matrix and you multiply the first row by 1, you get that same identity matrix. So every identity matrix can be attained from itself by performing multiplication of the first row by 1. Okay, so then there's that. And if you switch 2 rows, you also have a resulting matrix, which is an elementary matrix. Okay, so that's another example. Okay, the next theorem is theorem 1.5.1. And so that theorem says that row operations by matrix multiplication is the title of it. Okay, so if the elementary matrix E results from performing a certain row operation on I sub m, the m by m identity matrix, and if A is an m by n matrix, then the product EA is the matrix that results when the same row operation is performed on A. Okay. So what does that mean? Okay, so it's saying this, theorem 1.51, if the elementary matrix E results from performing a certain row operation on I sub m, and if A is an m by n matrix, then the product EA is the matrix that results from the same row operation when the same row operation is performed on A. So let's look at an example. So an example would be the following. Let's say you have the matrix. Let's say you have the matrix A, which is this. Let's say the matrix is 1, 1, 1, 2, 2, 2, 3, 3, 3. Okay. Now let's say the E matrix is the following. It's I'm going to switch the first and second row of the 3 by 3 identity matrix. Okay, so that's E. This is an elementary matrix because I just switched the first and second rows of I sub 3. Okay, if you look at EA, if you multiply E times A here, 0, 1, 0, 1, 0, 0, 0, 0, 1 times that matrix A, and see what you get. And so now I just chose this example at random. I didn't choose it intentionally because it would work out. I just chose the first matrix that popped into my head. Okay, so let's see what happens. So if I multiply first, so I get this entry is a 2, first row, first column, a 2, first row, second column, first row, third column, second row, first column, second row, second column, second row, third column, third row, first column, third row, second column, third row, third column. And so now you can see that what happens is EA is the matrix that if you looked at A and you switch the first and second row. So here are the first 2 rows of A, and here are the first 2 rows of EA. They're switched. The difference between A and EA is that the first and second row switch, the third row is the same. So E, the elementary matrix E, is the matrix you get from the original 3x3 identity matrix. And then you switch the first and second row, and then you get E. So if you switch the first and second row, you switch those 2 rows and get E. By R, I mean row. So R1 means row 1 and R2 means row 2. So switch R1 and R2 means switch rows 1 and 2, and you get E from the identity matrix. This is I sub 3, right? So from I sub 3, you get E by switching the first and second row. And so the effect you have on a matrix by left multiplying it by this E is that you switch the first and second rows of that matrix. That's what the theorem's saying. But it's not just true for this these matrices, these sizes, or this row operation. It's true for any elementary matrix, any elementary row operation. Okay, so this is a general statement. That's an example of one specific application of that statement. Okay. Okay, so now let's again, I want to look at something else. So now let's just talk about, this is example 3. And example 3 is row operations and inverse row operations. Okay, so if you start with the matrix 1, 0, 0, 1, and let's say you multiply the second row by 7. Okay, so what I did there was I multiplied the second row by 7. The opposite effect would be multiplying second row by 1/7, and you get back to where you started. So this is an example of, so here I'm going to write 7R2. I'm multiplying the second row by R2. Okay, as 7R2, that means multiplying the second row by R2. And then here I'm going to write 1/7 R2, and that's shorthand for multiplying the second row by 1/7. Okay, and then you get back there. So this second operation is an inverse. 1/7 times R2 is the inverse row operation of multiplying row 2 by 7. So if you perform a row operation and then an inverse row operation, you get back to where you started. See, if you start from here and you end here, we ended up at the same place. Okay, so if you also start with a 2x2 identity matrix 1, 0, 0, 1, and if you okay, so I'm just throwing error there. Okay, so now So now here we can switch the first and second rows. So if you switch the first and second rows, if you take this row and you switch it, then you get 0, 1, 1, 0. And so this is just switch R1 and R2. Though I'm also going to adopt this notation for switch R1, R2. R1 with arrows going back and forth here. That means switching R1. That's my shorthand for switching R1, R2, okay? So you can write out the words. If you write that, then I'm going to understand, but write it above the arrow, and then I'll understand you mean that you're switching in 2 rows. Okay, so now take this matrix, and I want to get back to the identity matrix. And so what to do is switch the same 2 rows. So if I switch row 1 and row 2 again, if I switch row 1 and row 2 again, then I get back to where I started. And so the inverse operation of switching rows 1 and 2 is the same operation switching rows 1 and 2. You switch row 1 and 2, then you switch row 1 and 2 again, you get back to where you started. Okay, and so also if you start with the identity matrix 1, 0, 0, 1, and you perform an elementary row operation on it, and you get this matrix, which is 1, 5, 0, 1. What you did was you added 5 times. You added 5 times row 2 to row 1. So by 5 R2 plus R1, I mean you're adding 5 times row 2 to row 1. And so the effect is changing row 1. You're changing the thing you're at. The thing you're multiplying by a constant staying the same, you're adding it to row. Okay, so now row 1 is changed. And so now the inverse operation of that, to get back to where you started, you want to get back to this one. And so you ask yourself, what is the inverse operation of that? Well, if I gave row 1 5 times R2, then the reverse effect would be removing 5 row 2s from R1. So the opposite of 5R2 plus R1 is negative 5R2 plus R1. Okay, if I take negative 5 times the second row and I add to the first row, if I take negative 5 times this row and add it to the first row, I end up with 1, 0 again, right? Negative 5 times 0 plus 1 is 1. Negative 5 times 1 is negative 5. Negative 5 plus 5 is 0. Okay, anyways, you see that there. So the effect, so now we have that these 2 operations are inverses of each other, right? Okay, and so we get back to where we started in each of those 3. These are examples of each elementary row operation and an example of their corresponding inverse operations. Okay. Okay, so illustrations of this on the whiteboard. Okay, next is theorem 1.5.2, and that says that every elementary matrix is invertible, and the inverse is also an elementary matrix. Okay, so proof. So I'm saying every elementary matrix is invertible, and the inverse is also an elementary matrix. So the proof is if E is an elementary matrix, then E results from performing some row operation on an identity matrix I. Let E not be the matrix that results from performing the inverse of this operation on I. Okay, so if E is an elementary matrix, then E results from performing some row operation on I, elementary row operation on I. Let E not be the matrix that results from performing the inverse of this operation on I. Applying our previous theorem, applying theorem 1.5.1, and using the fact that inverse row operations cancel the effects of each other, it follows that. So what follows is that if you take E naught times E, it's equal to I. So what's happening is that like for instance, E would perform a certain elementary row operation. If you multiply a matrix, this is E naught E equals I. Yeah, like for instance, if you had a matrix A, and you multiplied it on the left by E, right? That would be like performing an elementary row operation on A. But then if I then did E naught would be like then performing the inverse of that operation on the same matrix. And so the effect would cancel each other out and you would end up with the same matrix A. So starting with the matrix A, E would multiply on the left by E would be performing an elementary row operation on it. Multiplying on the left by E naught would be forming the inverse of that elementary row operation on EA, which would then cancel the effect E had on it, and you get back A. So what happens here? You multiply by E naught E on the left by any matrix A, and you get A. This E naught E is the identity. Okay, and so E naught E is equal to I, and so that's what I'm writing there. Okay, but it's also true by very similar reasoning. It's also true, and E naught is also equal to I, but almost the exact same reason. E naught is also equal to I. Multiplying the matrix on the left by E naught would be performing the inverse row operation, and then on the left, would be multiplying the left by E afterward would be performing the original operation. It doesn't matter the order. If you do an operation, then it's inverse, or it's inverse and then the operation, they cancel each other out in either order. And so E naught is also equal to the identity matrix. And so what happened here is just you thus the matrix E, thus the elementary matrix E naught is an inverse matrix of the elementary matrix E. So we found that an elementary matrix E has an elementary matrix E naught has an inverse. So every elementary matrix is invertible. It has an inverse, and the inverse is also an elementary matrix. And that's that E naught is describing this part. The inverse is also an elementary matrix, E naught. And every elementary matrix is invertible. That's the E, and it's invertible because we found a matrix E naught such that both equations are true. Okay, so that proves that theorem. Okay. Next is called the equivalence theorem. This is very important. In fact, it's so important that we're not even done. I can't even tell you the whole theorem right now. We're going to have to build on this theorem as the semester continues. Okay. So the theorem is saying that the following are equivalent statements. That a list of statements are equivalent. If A is an n by n matrix, then the following statements are equivalent. That is, all are true or all are false. Okay? Saying statements are equivalent are saying they're all true or all false. They're all the same in truth values. So statement A is that a matrix A is invertible. Statement B is that the equation AX equals 0 has only the trivial solution. Okay, to remind you, the trivial solution is the one in which all the unknowns in the vector X are 0. Okay, even though the equation AX equals 0 is a matrix equation. A is a matrix, but X is also a matrix. X is a column vector where its components are unknowns. Okay, so X is really a matrix consisting of a column of unknowns, and saying that it only has a trivial solution is saying that X as a column vector is the zero vector, meaning all the unknowns, all the entries of this matrix little x are zero. That's saying all the unknowns are zero. Okay. The trivial solution is where all the components of this vector X, all the components of all the entries in this matrix X are zero. Okay. That's what it means by trivial solution. C, the reduced row echelon form of A is I sub n, the n by n identity matrix. Okay. And D, A is expressible as a product of elementary matrices. Okay. I'm going to move this to the next page. Right there. Sorry. So that's the equivalence theorem. This is theorem 1.5.3 equivalence statements theorem. If A is an n by n matrix, then the following statements are equivalent. That is, all are true or all are false. A is invertible. B, AX equals 0 has only the trivial solution. C, the reduced row echelon form of A is I sub n. D, A is expressible as a product of elementary matrices. Okay. So let's prove it. Okay. Okay. Maybe no, we don't have a lot of time. Okay, so let's look at the proof. So we will prove the equivalence of these four statements by establishing a chain of implications. Okay, so what we want to prove is that statement 1 implies, sorry, not statement 1. Statement A implies statement B, and that statement B implies statement C, and statement C implies statement D. I think you see where I'm going here. And statement D implies statement A. Okay. So that's the goal of this proof. If we show all these implications, that A implies B and B implies C and C implies D and D implies A, that means that all the statements are equivalent. Okay, so another way that that's illustrated is that if you have statements A, B, C, and D, the goal is to prove that A implies B, B implies C, C implies D, and D implies A. And if that's true, then every statement implies every other statement, and vice versa. And so then that means that they're equivalent. So for instance, A implies B and B implies C, so A implies C. But C implies D and D implies A, so C implies A, right? So this one diagram, this one picture is if you look at particular cases, A would imply C in this chain, but C would also imply A. And so that means that A and C are equivalent. Okay, but there's nothing special about A and C. If you take any two of these statements, you choose any two you want, any two different statements here, you could show each implies the other, and that means that they're equivalent. Okay, and so that's why if we prove that goal, then we are done showing that all four of these statements are equivalent. Okay, so that's the goal. We want to show these. So it's really, every time you see an arrow, that's a separate statement to be proved. A implies B was the first arrow. The second arrow is B implies C. The third arrow is C implies D. And the fourth arrow is D implies A. So we have four things to prove, each of those four implications. So the first implication we want to prove is that A is that lowercase a implies lowercase b. Okay, so we want to prove that. So assume that A is invertible. Okay, right? That's what we're doing, right? So in order to say that A implies B, we have to assume statement A is true and then deduce that statement B is true. So we assume statement A is true, that A is invertible. Assume that A is invertible. let x naught be any solution of ax equals 0. Okay, multiplying both sides of this equation by the matrix A inverse, because A is invertible. So since A is invertible, we can talk about a matrix A inverse, and we can multiply by A inverse. If A is not invertible, we can't do this. If we don't know that whether or not A is invertible, we can't assume that it is and do this. And so, but because we're assuming A is invertible, we can multiply both sides of the equation by A inverse. Okay, so multiplying both sides of this equation by A inverse, you get that, well, if you multiply the left side by A inverse, then you get the left side is x. If you multiply the right side by A inverse, it's still 0. You get that x equals 0. Well, you get that x not equals 0. Okay. Okay, so just to, so I wrote that briefly there. I'm going to add to it here. If you have ax equals 0, ax not equals 0, and ax not is a solution of this equation. A is invertible, right? We assumed A is invertible. So I'm going to multiply the left side by A inverse. Okay, right, this is invertible. This is a solution of this equation. We want to see what form this solution can take. And so we're just assuming an arbitrary solution of this equation. So ax not equals 0, where A is invertible and x naught is the solution of that equation. Since A is invertible, we can talk about an A inverse. So I multiply both sides on the left by A inverse, which I'm allowed to do. And so A inverse ax naught is equal to A inverse times the 0 matrix. But now A inverse ax naught, without writing parentheses, you're kind of what you're saying kind of is that since we multiplied originally on the left, right? What we did was originally is that we multiply on the left by A inverse. And so by multiplying on the left by A inverse, then we're saying that we're multiplying the left by A inverse, right? So that's the first operation is A times x naught in the beginning. But we can switch the order of it by our properties that we went over earlier. And so that's equal to A inverse A times x naught afterwards. A inverse A is the identity matrix because it's a product of inverse matrices. You have I x naught. The identity times any matrix is that matrix, so it's equal to x naught. But we already have ax naught. We have that this thing is equal to A inverse 0 from earlier. So since A inverse times ax naught is equal to x naught, then what we have is that x naught is equal to A inverse 0, which is 0. And so what we have is that assuming that x naught is the solution of the equation, that implies that x naught equals 0. And so the final implication of all this is that our final conclusion is that every solution of the original equation must be 0. In other words, 0 is the only solution, right? Assuming that something is the solution of that equation, it implies that that solution is 0. So that means that the only solution to the equation is x naught equals 0. Okay. So x naught, so x, the only thing the little x vector can be is 0. That's the trivial solution. Okay, so the only solution of the equation ax equals 0 is the trivial solution. By trivial solution, I mean little x is equal to 0. Okay, and so we just proved statement B that ax equals 0 is only the trivial solution. Okay, so A implies B is now proven. The next thing to prove is that statement B implies statement C. Okay, so next we want to prove that. So we assume statement B is true. So assume that AX equals 0 has only the trivial solution. Okay, so we want to assume that. And we want to deduce from that, we want to show that that implies that the reduced echelon form of A is I sub n. Okay, so let's so let AX equal 0 be the matrix form of the system 1 on the whiteboard. So I'm going to move over to the whiteboard. Okay, so I'm going to do B implies C on the whiteboard because it helps writing. So let's go to the whiteboard. Okay, so in fact, I'm just gonna, let's just do the whole thing here. Okay, so where is it? So we want to prove that B implies C. Proof of that. Okay, so let AX equals 0 be the matrix form of the system below. Okay, so that system is A11X1 plus A12X2 plus dot 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 plus A1 and XN is equal to 0. A21X1 plus A22X2 plus dot 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 plus A2 and XN is equal to 0. Dot dot dot. Dot there. Dot dot dot. And then AN1X1 plus AN2X2 plus dot 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 plus ANNXN is equal to 0. Okay, so we have that system. Remember, the indices are describing which coefficient it is. So the first index is telling you which equation the coefficient is in, right? So A11, because the first index is a 1, that means that it's a coefficient in the first equation. A21, since the first index is a 2, it's telling you it's in the second equation. See how all of these are 1s because they're in the first equation. All of these are 2 because it's in the second equation. All of these are n because it's in the nth equation. So the first index is just telling you which equation the coefficient is in. The second coefficient is telling you which unknown it's next to. So the second coefficient being a 1 means it's next to the first coefficient. The second index being a 1 means next to the first one. The second one means next to the first unknown. The second coefficient being a 2 means it's next to this x2. Second index being a 2 means the next x2, dot, dot, dot. Second index is a 2, next x2, dot, dot, dot. The second index is an n, next to xn, n next to xn, n next to xn. Okay, so you see how the purple and green ones, they all matches perfectly. Each coefficient is labeled appropriately. And what's happening is that if I tell you 8, is that it matches. So you know exactly where each of them goes. Okay, so then it doesn't describe any. A32 is a specific coefficient there. It's not a different one, right? So it's well defined, and see it establishes each specifically what each coefficient is. Okay, so this is the system labeled as 1. Okay, and so what we're going to do is we're going to assume it has only the trivial solution. Okay, assume the system above has only the trivial solution. That's B, saying that AX equals 0 has only the trivial solution. If we solve by Gauss-Jordan elimination, then the system corresponding to the reduced row echelon form of the augmented matrix will be okay. So and so what happens is, if by Gauss-Jordan elimination, if you simplify the system, you're going to get x1 is equal to 0, x2 is equal to 0, and so forth, xn is equal to 0. Okay, I think you have to, with enough experience with Gauss-Jordan elimination, you can see how that would happen. If you went through all the steps of Gauss, if I went through all the steps of Gauss-Jordan elimination, I could show you that this is what happens. But it's what happens. If you take your original system, this system, and it only has a trivial solution, then all you have to do is do Gauss-Jordan elimination, and you will get this. And so what does this tell you? This tells you that thus the augmented matrix for the original linear system can be reduced to the to the augmented matrix where you have 1, 0, 0, ... 0, and then this is the column of zeros here at the end. Second row has 0, 1, right? Because the ones are corresponding with the x's here, and ... 0, and then that's still a 0, and then this continues. The last row is 0, 0, 0, ... The last one's a 1 because the x, but then this is still 0 because the rightmost entries are all 0, right? And so originally, if instead of thinking of the system and then reducing it to that system at the end, instead you could think correspondingly of the augmented matrix of this system, corresponding to this system, getting it to reduce row echelon form and getting this bottom matrix here. Okay. And so thus the augmented matrix for the original linear system can be reduced to the augmented matrix, that augmented matrix, by a sequence of elementary row operations. Okay. So ignoring the last column, we're ignoring the last column because our original matrix in reduced row echelon form is not the entire matrix. Instead, it's the left of this vertical line. To the left of the vertical line is the coefficient matrix in reduced row echelon form. So the last column has nothing to do with the coefficient matrix. The coefficient matrix is describing to the left of the equal signs. And so it's describing to the left of that vertical line. Ignoring the last column, we have that the reduced row echelon form of A is the identity, is I sub n. I'm just going to write a subscript n here, I sub n, period. Okay, so so what we did was this is showing that the original coefficient matrix capital A here is the coefficient matrix describing the coefficients on the left-hand side of the equal sign. When we get this linear system, when we simplify it as far as we can go, we get this final linear system. Correspondingly, it's telling us that the coefficient matrix of the original system, when doing elementary row operators, getting it to reduce echelon form, we get the left side of this. To left this vertical line, we get the reduced echelon form of A is the n by n identity matrix. These ones are on the main diagonal. So this is an n by n identity matrix. Okay. Okay, and so that's the proof that C and B implies C. Okay. The proof is there. Okay. So C implies D is next. So we have to prove C implies D. So we assume C. Assume the reduced row echelon form of A is I sub n. That means that A can be reduced to I sub n by a finite sequence of elementary row operations. So let me explain this again. I said this before, I'll repeat again. So assume the reduced row echelon form of A is I sub n. That means that A can be reduced to I sub n by a finite sequence of elementary row operations. Okay, so we said earlier, right? So A, we're assuming that if we start with A and we perform a sequence of elementary row operations on it, we can get to the identity matrix. That's statement C, right? Oh, sorry. We assume that the reduced row echelon form of A is I sub n. Well, if the reduced row echelon form of A is I sub n, how do we get the reduced row echelon form of a matrix? By performing elementary row operations on it. When I taught you Gauss-Jordan elimination, we started with the matrix. We found its corresponding. We started with well, we might start with a linear system. Look at its corresponding augmented matrix. Then with that matrix, by elementary row operations, following a certain procedure, an exact procedure, we get the identity matrix. It ended, that procedure ends, right, in finite time, right? We finished doing it, right? There are only finitely many elementary row operations that we have to do in order to get any matrix to the identity matrix. And so when you can reduce a matrix A to reduce row echelon form, you can perform Gauss-Jordan elimination, which involves finitely many steps, finitely many elementary row operations on that matrix to get it to the identity. Okay, so we can now assume that we can get to the identity matrix after performing finitely many elementary row operations on A. Okay, I said that fast, but that makes sense. Okay, so I'm saying that A can be reduced to IN by a finite sequence of elementary row operations. So by theorem 1.5.1, each of these operations can be accomplished by multiplying on the left by an appropriate elementary matrix. Theorem 1.5.1 was the one that said that you can capture an elementary row operation by multiplying it by an elementary matrix. It's this one. This. Okay. If the elementary matrix E results from performing a certain row operation on I sub m, and if A is an n by n matrix, then the product EA is the matrix that results from when the same operation is performed on A. Okay. Okay. So what's happening here is that So when we go from A to I sub n, instead of performing elementary row operations on A to get to I sub n, we can just keep left multiplying A by the elementary matrix that results in that row operation being performed on it. So every time we would do an elementary row operation on a matrix towards getting it to reduce echelon form, instead of performing the elementary row operation, we left multiplied by an appropriate elementary matrix whose effect is performing that elementary row operation on it. Okay. So by theorem 1.5.1, each of these operations can be accomplished by multiplying the left by an appropriate elementary matrix. Thus, we can find elementary matrices E1, E2, ... E sub k, such that the following happens. If we multiply EK, E sub k minus 1, ... E sub 2, E sub 1, in that order, A is equal to I sub n. I'm going to call this equation 3. I'm not multiplying by 3. I'm just denoting it by 3. If I want to refer to this equation again, refer to it as equation. Okay, close. So how does this happen? If I start with A, right, I can perform elementary row operations on it to get to I sub n by Gaussian elimination. But each time, instead of each time doing an elementary row operation, I left multiply it by an appropriate elementary matrix, which by left multiplying by that elementary matrix, the effect is doing the same elementary row operation on that matrix. So instead of performing finitely many elementary row operations, say k many, I left multiply by k appropriate elementary matrices. Okay, so instead of doing the first elementary row operation, I left multiply by E1. Instead of doing the second elementary row operation after the first one, I left multiply by E2 after left multiplying by E1. And so I continue that until I left multiplied by E sub k at the end. The effect of this product is that I get to the identity matrix. Okay? Because we know we can get to an identity matrix using Gaussian elimination, and we know that there are only finitely many elementary row operations we have to do to reach the end of Gaussian elimination. Okay? By the way Gaussian elimination is defined, right? We're defining it in such a way that it can only have finitely many steps, because our original matrix has only finitely many rows and columns. And so because we're dealing with matrices with finitely many rows and finitely many columns, the way Gaussian elimination is set up is that we reach the end in finitely many steps. Okay. So by theorem 1.5.2, E1, E2, ... E sub k are invertible. We had the theorem that said that all elementary matrices are invertible, and it also said that their inverses are also elementary matrices. So by theorem 1.5.2, E1 to EK are invertible. Multiplying both sides of equation 3 on the left successively by EK inverse, E sub k minus 1 inverse, ... in this order. And then lastly, E sub 1 inverse. So multiplying both sides of equation 3 on the left successively by EK inverse, EK minus 1 inverse, ... E1 inverse, we obtain that A is equal to, so you know, I'm going to show this on the whiteboard. We have this equation here, right? We have this equation here. And so I'm going to start with that equation and show you how we get the result. It's easy. This step is easy. I understand the whole thing is not easy, but this step is easy. Okay, if you start with, so we're starting with ek minus 1 dot 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 e1 a equals I sub n. We're starting with that, and we're successively multiplying the left by the inverses of the elementary matrices. And so now I'm going to write smaller. So we have this already. So we're going to left multiply by ek inverse, ek minus 1 inverse dot 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 e1 inverse. And we're multiplying both sides by that same quantity. So I left multiplied the left side by that, and now I'm going to left multiply the right side by that same thing. So I'm now left multiplying by ek inverse. To save space, make sure I don't run out of space, I'm just going to not include the ek minus 1 inverse. It's in the dot dot dot. Okay, so I left multiply and the left both sides by that. Well, now what happens is that by the way I chose this product, the ek cancels with the ek inverse. The ek minus 1 cancels with the ek minus 1 inverse. Everything that dot 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 cancels with these in one at a time. And the e then cancels, e1 cancels with e1 inverse. And so all these things cancel. And so on the left side, the only thing we have left with is a. The only thing that's left on the left side is a, and on the right we have left a is equal to e1 inverse dot 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 ek inverse I sub n. Well, multiplying by the density doesn't change anything, so this is equal to e1 inverse dot 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 e sub k inverse. So we just showed is that a is equal to the product of those inverse elementary matrices in that order. Okay? Make sense? So we obtain that A is equal to what I just wrote down, E1 inverse, E2 inverse, dot, 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 E sub K inverse. I'll denote this by equation 4. Okay. By theorem 1.5.2, this equation expresses capital A as a product of elementary matrices. That is because it says that the inverse of every elementary matrix is also an elementary matrix. Okay, so E1 inverse is only the inverse of an elementary matrix. Even though we're using the symbol E, doesn't directly mean that it's an elementary matrix, but it actually is, so the E is fine, but it's because of this theorem we know that E1 inverse is an elementary matrix. It says that the inverse of any elementary matrix is an elementary matrix, right? Just writing this down is saying we have the inverse of an elementary matrix. By a theorem, it's also elementary, and so we're now expressing A as a product of elementary matrices. And so that's what we want to show in D. Statement D is that A is expressible as a product of elementary matrices. We assume that the reduced echelon form of A is I sub n. Assume the reduced echelon form of A is I sub n, and we concluded that A is expressible as a product of elementary matrices. Right there. Okay, so C implies D is proven. And lastly, it's D implies A. Okay, so D implies A is the last thing to prove. And then we are done with the chain of implications, proving the chain of implications. And so we proved that all 4 statements are equivalent after we prove this. So we assume A. So we assume that that A is expressible as a product of elementary matrices. Okay, that's statement D. A is expressible as a product of elementary matrices. So we're assuming D. And so we want to show that implies that A is invertible. Okay, so from theorems 1.4.7 and 1.5.2, the matrix A is a product of invertible matrices because every elementary matrix is invertible. And so the matrix A is a product of invertible matrices, and hence is invertible. A product of also a product of invertible matrices is a product of invertible matrices is also invertible. Okay, so first we have A is expressible as a product of elementary matrices. Each of those elementary matrices by theorem is invertible. So now A is a product of invertible matrices. And by another theorem, the product of invertible matrices is also invertible. And so we now conclude that A is also invertible. Okay, so I'm just going to write that quickly on the whiteboard, right? We assume that A is a product of elementary matrices. So A is equal to E1, E2, ... E sub k for some k, right? And so A is a product of elementary matrices, but each E is invertible by theorem. Every elementary matrix is invertible by theorem. So now A is a product of invertible matrices as a product of elementary matrices, right? It's a product of invertible matrices. By theorem, if you multiply invertible matrices, you get another invertible matrix. And so now this is itself an invertible matrix. Make sense? Okay. So that theorem is that's very quick to prove. Okay, and so D implies A is all proved. We've proved A implies B, B implies C, C implies D, and D implies A. And so since we achieved our goal of proving all those implications, we've now proven that all four statements are equivalent, but either they're all true or all false. Okay, and so this is a very powerful theorem. Even though it does not say that any of these statements are true or any of these statements are false, if you know one of them is true, then you know all of them is true. If you know one of them is false for a matrix, you know all of them are false. So for instance, if you want to show that the reduced echelon form of a matrix is the identity I sub n, well, if you can show it's invertible, then you've also shown that its reduced echelon form is I sub n. Okay, so now when you want to find one of these things to be true, instead of showing that's true, you could show one of the other things is true. Or if you find one of them is false, you then realize that what you're trying to show is false. Okay, so it's a very powerful theorem. Okay, so that proof is done. It's a long proof. Good. So now we go on to another topic, and the topic is a method for inverting matrices. Yes, this is a different, we're done with that theorem and proof. So a method for inverting matrices. So assume A is an invertible n by n matrix. It's a square matrix. Okay. In equation 3, here in this equation, in equation 3, the elementary matrices execute a sequence of row operations that reduce capital A to the identity matrix I sub n, right? You start with A, and then you keep performing elementary operations or left multiplying by an elementary matrix until you get to the identity. Okay, so that's true. If we multiply both sides of this equation on the right by A inverse and simplify, we obtain So we're going to multiply on the right by A inverse. So we're going to multiply this on the right by A inverse and this on the right by A inverse. So this A will cancel with the A inverse. And on the right, an identity matrix times A inverse is A inverse. So we're going to get A inverse on the right side, and then we're going to get the product of these elementary matrices on the left side. So what we obtain is that the product of these matrices is equal to A inverse, right? So we just multiply the right both sides by A inverse. Right, that's our original equation. You multiply on the right by A inverse, both sides on the right by A inverse. And so if you multiply both sides on the right by A inverse, the A inverse cancels the identity, and then multiplying the identity doesn't have an effect. So you have this on the left side, and on the right side, you have identity times A inverse, which is A inverse. So you get that, right? So you have the A inverse is equal to that product. Okay, but this sequence, this equation tells us that the same sequence of row operations that reduce capital A to I sub n will transform I sub n to A inverse. Okay, so if you start with A, so this is the conclusion. This equation tells us that the same sequence of row operations, this sequence from right to left, it goes from right to left. So E1 is the first one, E2 is the second. It says that the same sequence of row operations to reduce A to I sub n will transform I sub n to A inverse. Oh, sorry. I need the I sub n there. Okay, so A inverse is the identity. Okay, so if you start with the identity and you perform these K elementary row operations on it, you get A inverse, right? But this product is the same product that you perform on A to get the identity. So this product gets you from A to the identity. It also gets you from I sub n to the A inverse. Okay. And so, okay, so thus we have established the following result. Okay, and this is called the inversion algorithm. To find the inverse of an invertible matrix, capital A, find a sequence of elementary row operations that reduces capital A to the identity matrix. And then perform the same sequence of operations on the identity matrix on I sub n to obtain A inverse. Okay, so if you find a sequence of elementary row operations that reduces A to the identity matrix, then if you start with the identity and you perform the same sequence, you get A inverse. Okay, and so there is a nice way to do this procedure, and so I'm going to show you that. Okay, so that's going to be this next example. So what we're illustrating is this inversion algorithm. So I'm going to move this inversion algorithm to the whiteboard. It's the same thing. I'm just copying and pasting it. Let me see if it comes out all right. It did. Okay, but this caret means A inverse. Okay, is that clear? So and this is I sub n. This is I sub n, and this is A inverse. That's this. Okay. Right. oops. This is right A inverse. This is I sub n. Okay. To find the inverse of an invertible matrix A, find a sequence of elementary row operations that reduces A to the identity matrix, and then perform the same sequence of operations on I sub n to obtain A inverse. So if you have a sequence of elementary row operations that goes from A to In, perform the same sequence on In to get A inverse. By 1 arrow, the 1 arrow is representing many, possibly many elementary row, a sequence of elementary row operations. Okay. What I'm going to do is I'm going to use colors to illustrate this. So I don't want to erase everything. Okay. So this arrow I'm going to draw here. Let's go green. This green arrow, no, straight arrow. This arrow I'm performing here is a sequence of elementary row operations that reduces A to the identity matrix. Okay, so it's a sequence of elementary row operations that reduces A to the identity matrix. Do that same sequence in In, and it reduces In to A, and it gets In to A inverse. Okay, so now let's look at example 4. So example 4 is using row operations to find A inverse. It's not A, it's A inverse. So I'm just going to write it in here. Find A inverse. Okay. So our original matrix is, we want to find the inverse of this matrix. So A is this 3 by 3 matrix. It's 1, 2, 3, 2, 5, 3. 1, 0, 8. Okay, so we want to use row operations to find the inverse. Okay, so our solution, I'm going to describe the solution, how we're going to do that here. So, we want to reduce A to the identity matrix by row operations. And simultaneously perform the same row operations on the identity matrix. To produce A inverse. And I'm not done typing, I'm going to put an inverse symbol. To produce A inverse, okay? So we want to reduce A to the identity matrix by row operations. For I sub 3, to just help you out here, we want to reduce A to the identity matrix by row operations and simultaneously perform the same row operations on the identity matrix to produce A inverse, okay? So we can reduce this matrix to the identity by elementary row operations. But as we do that, we just want to correspondingly also perform the same elementary row operations in the same order on I sub 3. And the result, when we reach the end step, when we reach I sub 3 here, we will correspondingly reach A inverse there. So the signal to stop this process is when A reaches I3, that means I sub 3 reaches this unknown matrix A inverse. And then we will have found A inverse. Okay. Okay, so to accomplish this, we will adjoin the identity matrix to the right side of capital A. We thus produce the partitioned matrix of the form. And so the matrix is of the following form. So we have a matrix A. We partition this matrix where on the left it's A and on to the right it's the identity matrix, where it's an n by n identity matrix of the same size as A. Okay. So we're joining the identity matrix to the right of A. We have a larger matrix where we partition to two parts. The left side is A and the right side is I. Then we will apply row operations to this matrix until the left side is reduced to I, the identity matrix. These operations will convert the right side to A inverse. I'm not done. I'm going to put a little inverse symbol here, A inverse. So the final matrix will have the form. It'll have the form where on the left side, it's the identity matrix. On the right side, it's A inverse. Okay. So that's the end of the description of this procedure. Okay, so to accomplish this, we join the identity matrix on the right side of A. Left is A, right is I. And so what we do is we start with our matrix A. Sorry, excuse me. A sequence of elementary row operations will get A to I, and correspondingly, I will go to A. So once the left side has I in it, we've now done the procedure of getting A to I, which means we know that that same exact procedure must have gotten I to the A inverse matrix. And so when the left side is I, we stop, and that means whatever is on the right side, if we did this correctly, is A inverse. If you do it incorrectly, then A inverse might not be on the right side, right? But assuming everything's done correctly, then you have A inverse on the right side. All right, so that green thing is going to stay there. Okay, so so that's how the procedure works. So class ends at 9:50, which is less than a minute from now. So we're going to stop here. And so next class, we will look at an example. We'll start the class with an example. The beginning of the lesson will be an example of how this is done. Okay, so next class, we will illustrate this procedure by an example. Okay. Okay, so next class we will give an example of this. So I'm going to save this. Save the whiteboard. Okay. Don't go yet. I still okay, so we are still on 1.5. So I can't assign homework right now. Okay, so there's no homework for Thursday. Okay. So I'm not announcing the first exam yet because we still have a lot more material to cover for the first exam. There's still some time before. So you'll have at least 2 weeks advance notice of the first exam. Okay. I'll stop here. It's now 9:50. And so I'll see you on Thursday. Okay.